In this video, I'll be exploring 5 different concepts: trade winds, Chinnok winds, Foehn winds, Sirocco winds, and monsoons. Let's start with some key terminology: easterly winds, westerly winds, windward, and leeward.
Let's start with easterly and westerly winds.
When it comes to winds, we focus on the direction they originated, not where they're going. So winds that originate from the west are considered westerly winds, and winds that originate from the east are considered easterly winds. What wind is this? Northeasterly or southeasterly? Northeasterly, since it originates from the northeast. And that's easterly and westerly winds. Next we have windward and leeward. Windward refers to the side of a mountain that receives incoming prevailing winds or trade winds, whereas the leeward side of a mountain is the sheltered side that prevailing or trade winds flow down. The windward side of a mountain is wet since it brings lots of moisture and rain, whereas the leeward side of a mountain is dry since it receives little rain. You can see an example of windward and leeward sides of mountains on the islands of Hawaii. One side is wet and green, the windward side, and one side is dry and brown, the leeward side. And that's our key terminology. Now we're ready to start exploring our 5 concepts.
Trade winds. First, let's take a step back and talk about prevailing winds.
Prevailing winds are winds that almost always flow in the same direction. Trade winds are prevailing winds that largely always flow east to west along the Earth's equator region, otherwise known as easterly winds. They're called trade winds since any trade ships needing to travel west along the equator region would be assisted by said winds, hence the name trade winds. However, in addition to ships, these trade winds can also steer storms such as hurricanes. As you can see from this map, which highlights hurricane wind patterns across the globe, the direction is overwhelmingly east to west and along the equator region. Additionally, the Earth's rotating globe nature means that prevailing winds will be manipulated to give off the illusion of a curved path, when in reality they're following a straight path. This phenomenon is referred to as the Coriolis effect. Back in April of 2022, I uploaded episode 4 of my Flat Earth Debunked series, in which I cover the Coriolis effect in some detail to prove the Earth is a round spinning globe. Isolating a single stream of air and applying the Coriolis effect, we can combine all of these points to show that, as the Earth rotates, the trade winds from the north move along a curved path, but the intended path is still technically a straight path. I've put a link in the description for the full video if you're interested. So far we understand prevailing winds as winds that almost always blow in the same direction, and trade winds are easterly winds that, due to the Coriolis effect, give the illusion of a curved trajectory. But for the big picture on prevailing winds, we need to understand global atmospheric circulation. In Queen's 1981 classic, Under Pressure, Freddie Mercury sings the famous opening line, "Under pressure, pushing down on me, pressing down on you, no man has close." While this has nothing to do with atmospheric conditions, if you think of pressure in the atmosphere as something pressing down, then high pressure skies can be understood as having a great downwards force, so much so that it prevents the air from rising and condensing into clouds. On the flip side, low pressure skies experience no pressure at all. In fact, it promotes free upward movement to the point of cloud formation. A key component of this is that hot air rises because it's lighter, and cold air sinks because it's heavier. So skies full of clouds are low pressure skies, and clear skies with no clouds are high pressure skies. The magic formula behind global atmospheric circulation is that high pressure will always seek low pressure. Global atmospheric circulation refers to these regions where low pressure moves to high pressure as cells. These circulation cells move rising warm air and sinking cold air all across the globe, but in a predictable direction since they're prevailing winds, and, of course, prevailing winds virtually always blow in the same direction. There are 3 cells in each hemisphere, 6 in total. Either side of the equator is the Hadley cells, followed by the Ferrel cells, and then the polar cells at the top and bottom of the Earth. Remember, Peter fell hard, hard fell Peter. These cells each have a significant role in circulating air masses all around the globe, hence the term global atmospheric circulation. Let's break it down. The Hadley cells take warm air at 0 degrees and move it to 30 degrees north and south. The Ferrel cells then take that warm air at 30 degrees north and south and move it to 60 degrees north and south. From here, the polar cells take that warm air at 60 degrees north and south and move it to 90 degrees north and south. These cells are the prevailing winds, blowing primarily in the same direction always. Since our pilot requested I look at trade winds, let's have a closer look. We'll start at the equator, the region that receives the most direct sunlight. As this area heats up, it creates a zone of low pressure called the Intertropical Convergence zone. I made a video in May of 2022 on the Intertropical Convergence zone that covers this concept in some detail if you would like to know more. I'll leave a link in the description. Essentially, as the air in this low pressure zone along the equator rises, the air eventually sinks and becomes colder, creating an area of high pressure 30 degrees north and south. Since high pressure skies seek out low pressure, air at 30 degrees north and south will constantly try and blow towards the equator region. In an Earth that does not spin, this would be a straight line, but due to the curved rotating nature of the globe Earth, the Coriolis effect kicks in and creates an illusion that the path is curved. We can see this curved path all over the globe as a result. Focusing on the trade winds of the Hadley cells above and below the equator, this creates a constant easterly wind that will always blow east to west, hence being a prevailing wind. And that's trade winds. Chinnok winds. Next we can explore Chinnok winds. First we need to understand that Chinnok winds are prevailing westerly winds, meaning they almost always have the same direction, from west to east. Another key feature of these winds is that they require the presence of mountains to exist. When moist air approaches the windward side of a mountain range, they begin to climb the mountains, gaining altitude and becoming colder. The moisture in the air condenses and forms clouds, which rains on the windward side of the mountain. This type of rainfall is known as relief rainfall. This is because relief is the term used to describe the difference in height between 2 points. And this type of rainfall occurs exclusively due to a sudden increase in elevation between 2 points. As the air flows down the leeward side of the mountain, the air warms and the clouds begin to dissipate, creating a dry climate with very little rainfall. This area of dry climate on the leeward side is known as rain shadow, since, like shadows occur when light is intercepted by an object, this pocket of dry climate is created by mountains intercepting rain and creating a shadow of dry climate. This is why the windward side of a mountain range will be green and wet, and the leeward side will be brown and dry. You can see examples of this along the South Island high country of New Zealand, the Himalayan mountain ranges of Nepal, the Ankaratra Mountains of Madagascar, and the Sierra Nevada mountains of the United States. But now that we understand all our required background knowledge, we can focus in on Chinnok winds. Simply put, as the air descends down the leeward side of the mountain ranges, it warms and becomes dry. This warm, dry, descending air is what's known as Chinnok winds. These winds can melt a foot of snow in one day, and, in the absence of snow, can dry up vegetation. One harsh impact of Chinnok winds is that rain-shadowed areas that are already deprived of rain, and thus dry, will have these dry conditions exaggerated by the warm, drying Chinnok winds that flow down the leeward side of the mountain. Now what's cool about Chinnok winds is that they create a very unique cloud formation known as Chinnok arches. These winds are part of the mountain wave family and make very rare and beautiful clouds seen here. Let's break down how they form. Imagine I have a chain and give it a sudden upwards flick. The resulting flick creates a series of wave-like shapes moving up and down along the chain. We can see how after the initial arch, the wave pattern continues, some areas moving downwards and other areas moving upwards. But significantly, the arches get weaker as you move further away from the source of the original upwards flick. Now, instead of a chain, imagine a stream of wind. Once it encounters a mighty mountain, it gets flicked up suddenly by the mountain on the windward side, creating relief rainfall. As it goes down on the leeward side, the clouds disappear and creates rain shadow. Now remember, the wind rising and gaining altitude is what causes the moisture in the air to condense and form clouds. So after the initial arch over the mountain, as with our chain example, the wave pattern continues, going up and regaining moisture and creating clouds, then down, lowering in altitude and dissipating the clouds, then up creating clouds, then down dissipating them. and so on. You'll also notice them becoming weaker as they develop away from the mountain. You can see this pattern in time-lapse videos of Chinook arches. Here is where the wind goes up, forming clouds, here is where it goes down, dissipating them, and here is where they go up again. It can also be seen here, up and clouds, down and no clouds, and then up and clouds again. And here, in the Bald Eagle Valley of central Pennsylvania. Up in clouds, down and no clouds, then up in clouds again. One unique characteristic of Chinook arches are there are often sudden and sharp divides between clear sky and clouds. Now, what's important for our pilot is that this wave pattern creates rotors, giant gyrating pockets of cycling air which creates turbulence. Let's explore this by highlighting a pocket of air here. As the wind flow goes down the leeward side of a mountain, it creates rotors that rotate clockwise. Then, going up, creates rotors moving counterclockwise. And as it goes back down, creates rotors moving clockwise again. So if you're flying by a mountain, you can experience turbulence pulling you in one direction one moment, and quickly experience turbulence pulling you in the opposite direction moments later. Additionally, some of this wind stream will actually flow around the mountain, creating turbulence once you pass the mountain entirely. So don't be fooled into thinking escaping the mountains while flying will free you from their turbulence. You'll need to prepare for turbulence moving around the mountains too. And that's Chinook winds. Foehn winds. Now what are Foehn winds? Before I explain that, let's talk about pants, or underpants depending on where you're from. If you grew up in Australia like me, these are your pants, and these are your underpants. If you grew up in the United Kingdom like my wife, these are your trousers, and these are your pants. Same thing, but depending on where you're from, they have a different name. This same practice is observed with the leeward drying winds flowing down a mountain. We've already discussed how in North America they're called Chinook winds. However, if you're in the European Alps, they're called Foehn winds. If you're in Central Asia, they're called Afghanet winds. If you're in the Andes of South America, they're called Paloche winds. And if you're in Southern California, they're called Santa Ana winds. So Foehn winds are Chinook winds, but the mountains causing them are the European Alps. And that's Foehn winds. Sirocco winds. Next we have Sirocco winds. Sirocco winds occur mainly here, over the Mediterranean Sea, where the Ferrel and Hadley cells meet. Areas where prevailing winds meet are called convergence zones. At this particular convergence zone, you've got Ferrel and Hadley cells pushing down along North Africa, creating high pressure systems and causing little rainfall. But remember, high pressure is always moving towards low pressure. The Ferrel cells want to move the warm air to 60 degrees north, and the Hadley cells want to move the warm air to 0 degrees along the equator. Given that Sirocco winds are a weather event originating in North Africa and blowing across the Mediterranean Sea to southern Europe, we will only focus on the Ferrel cells. Normally, this movement of air masses by the Ferrel cells would be fine, but sometimes North Africa can have massive sandstorms that can reach 6 kilometers or 3.7 miles in height, filling the sky with hot, dry air full of sand and dust. This mass of sand and dust can get carried by Ferrel cells over the Mediterranean Sea and turn into visibility-reducing Sirocco winds. These Sirocco winds often continue to carry the debris towards Europe and cover parts of southern Italy and Greece in a thick, dusty haze. For our pilot, flying over southern Europe and the Mediterranean Sea during such conditions can cause major restrictions to visibility and trigger lots of turbulence, since the Sirocco winds can easily reach speeds of over 100 kilometers or 62 miles per hour. Looking at a dust forecast map taken from the Barcelona Dust Forecast Center, we can see how dust from North Africa moving towards Europe can cause significant dust coverage for countries like Greece. This is the equator line, these are the Ferrel cells, and these are the Hadley cells. Also, you may be asking why the Sirocco winds only mention Europe, when it clearly affects Africa also. That is because this is a Sirocco wind, and this is a Haboob wind. Same phenomenon, only a different name. Now, Sirocco winds are much more than just dust and sand in the wind. This is because sandy Sirocco winds moving over the Mediterranean can absorb moisture and cause heavy fog and rain. sometimes with a distinct blood red hue, hence the ominous term blood rain, given to Sirocco winds that mix reddish-orange sand and dust with moisture and condensation from the Mediterranean. If you want to learn more about blood rain, I've left a link from the infographic show in the description that covers everything. And that's Sirocco winds. Monsoons. Finally, we have monsoons. Monsoons develop depending on sun exposure, and since they occur mainly within the tropics, in other words, the space between the Tropic of Cancer and the Tropic of Capricorn, we need to familiarize ourselves with the Intertropical Convergence Zone, or ITCZ. I made a video in May of 2022 on the Intertropical Convergence Zone that covers all the basics in some detail if you would like to know more. I'll leave a link in the description. In that video, you'll learn how the sun heating up the ground, creating rainy low pressure skies, which then sink around 30 degrees north and south to form high pressure skies, is not a permanent condition, for 3 reasons. The Earth is on a tilt, rotates on its axis, and orbits around the Sun. This means that the solar concentration that creates that area of low pressure ranges from focusing on the Tropic of Cancer in July to the Tropic of Capricorn in January. That means that that area of low pressure will shift between the two, creating seasonal weather events throughout the year, such as, you guessed it, monsoons. Now for the big picture. We'll start in March, when the ITCZ is along the equator. As the year progresses and the sun is concentrating more of its energy towards Tropic of Cancer, so too will the ITCZ move to meet the area of solar concentration, bringing with it high levels of precipitation. Looking at a climate graph from India, you'll notice high levels of rainfall during the month of July as a result. The shift of the ITCZ to the north in July leaves the Tropic of Capricorn lacking the solar concentration it needs for low pressure, which means that high rainfall enjoyed in the north isn't around in the south, so the south will experience a dry season. Moving through the year, the sun will begin to concentrate its energy towards the Tropic of Capricorn by January. And now the south will experience a rainy season, while the north will experience a dry season. This can be noticed in Indonesia's climate graph, showing high levels of rainfall in January as a result. As a case study, we're going to focus on India as it's a primary figure in the famous South Asian monsoon. But keep note that monsoons occur in many different continents, but follow the same principle. Let's get started. In summer, India is exposed to lots of heat by the sun, creating an area of cloud generating low pressure over the land and an area of high pressure over the water. The critical detail is that the land heats up faster and more effectively than the ocean. And since high pressure seeks low pressure, the warm air draws in humid southwesterly winds from the surrounding oceans. This humid air reaches the warm land and rises and condenses into even more clouds. Additionally, to the north of India is Nepal and the renowned Himalayan mountains. If you recall when we studied Chinnok winds, mountains are notorious for creating relief rainfall on the windward side and rain shadow on the leeward side. So you've got additional cloud formation along the windward side of the Himalayan mountains. So to recap, you've got the sun heating up the land, creating low pressure, causing warm air to rise, condense and form clouds. Next, you've got moist, humid air being drawn in from the oceans, reaching the warm land, rising and condensing and forming more clouds. And then you've got mountains acting as a ramp that launches air upwards, gaining altitude, condensing and forming even more clouds. The significance here is that monsoon season has all 3 of these sources of rainfall occurring at the same time. These heavy rains can last from May through to September, and are typically seen as a welcome blessing to the land, as many locals depend on the monsoon for agriculture. However, the South Asian monsoon has 2 seasons: the summer monsoon that approaches from the southwest, and the winter monsoon that approaches from the northeast. The first thing you need to learn about the winter monsoon is that it is the opposite of the summer monsoon. This is because the ITCZ is now focusing its solar energy along the Tropic of Capricorn, meaning the low pressure skies are above the Indian Ocean, and now high pressure skies fall upon India. This high pressure prevents the formation of clouds entirely, and brings about a dry season. The high pressure skies over the land now seek out the low pressure skies over the ocean and blow northeasterly. This is significant for our pilot, since depending on the season, summer or winter, will determine what kind of winds are blowing, southwesterly or northeasterly, and the degree of cloud coverage and visibility and intensity of rainfall that you can expect. So if you're flying over India during summer between the months of May through to September, you can expect low pressure storms and high cloud coverage over the land, clear high pressure skies over the ocean, and with southwesterly winds blowing. And if you're flying over India during winter between the months of October through to January, you can expect clear high pressure skies over the land, low pressure storms and high cloud coverage over the oceans, and with northeasterly winds blowing. And that's monsoons. Thank you for watching. I need to apologize for the delay in uploading. I've had a very busy past 100+ days. I got married to the love of my life in early December 2022, and it took a mountain of work and months to plan for our big day, which meant most of my time was spent doing wedding things, not spent making videos. I've also started a new job in September, so I'm absolutely starved for free time. And I just came back from Iceland a week ago, so there goes my school holidays. And in any case, I promised our pilot that I'd make this video, and here it is. Hope it helps. Thank you, and please support the channel by subscribing, leaving a like, and leave a comment if you want anything you want me to cover in the future, any tests coming up. You know, I do enjoy making these. It's just my time is pretty limited at the moment. So drop me a comment of any information you'd like me to make a video on, and thank you for watching.